Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. The atmosphere of the Earth, which is composed of a mixture of gases that are held in place by the gravitational pull of the planet, exerts a continuous and largely imperceptible force upon every surface with which it comes into contact, and this force, when measured per unit area, is referred to as barometric pressure or, in many scientific and meteorological contexts, as atmospheric pressure, a quantity that has been the subject of sustained investigation and careful measurement for a period of nearly 4 centuries. The total mass of the atmosphere has been estimated to be approximately 5.15 times 10 to the 18th kilograms, which is to say roughly 5 million billion metric tons of gas pressing downward upon the surface of the Earth at all times. And it is the weight of this enormous column of air, extending from the ground to the outermost fringes of the atmosphere at altitudes exceeding 100 kilometers, that gives rise to the phenomenon known as barometric pressure. At sea level, under conditions that are considered to be standard, the atmosphere exerts a pressure of approximately 101,325 pascals, which is equivalent to 1,013.25 millibars, or 29.9212 inches of mercury, or 760 millimeters of mercury, or 14.696 pounds per square inch, or precisely 1 standard atmosphere. These various units of measurement, each of which has been developed in a different historical and practical context, all describe the same physical reality, which is that the air above any given point on the surface of the Earth is pressing down with a force that is, under average conditions, roughly equivalent to the weight of a column of water approximately 10.3 meters in height, or, equivalently, a column of mercury approximately 760 millimeters in height. The Pascal, which is the SI unit of pressure and is named after the French mathematician and physicist Blaise Pascal, who lived from 1623 to 1662, is defined as 1 Newton per square meter. And, because this is a rather small unit in the context of atmospheric measurements, it is common practice in meteorology to use the hectopascal, which is equal to 100 pascals and is numerically identical to the millibar, a unit that was introduced in 1909 by the British meteorologist Sir William Napier Shaw. The millibar, which is equal to 1,000th of a bar, which is itself defined as exactly 100,000 pascals, has been widely used in weather reporting and aviation for more than a century, and the transition from millibars to hectopascals, which was recommended by the World Meteorological Organization, has been a largely cosmetic change, as the numerical values remain precisely the same. In the United States and in certain other countries where imperial units remain in common use, barometric pressure is frequently reported in inches of mercury, a unit that derives directly from the earliest method of measuring atmospheric pressure, which involved the use of a column of liquid mercury in a glass tube. The standard atmospheric pressure of 29.9212 inches of mercury corresponds to a column of mercury that is approximately 760 millimeters, or 76 centimeters, in height, and this measurement has been in use, with only minor refinements, since the middle of the 17th century. The density of mercury, which is approximately 13,595.1 kilograms per cubic meter at a temperature of 0 degrees Celsius, is what makes it a particularly convenient liquid for use in barometers. As the height of the column required to balance the atmospheric pressure is of a manageable size, unlike water, which would require a column of approximately 10.3 meters in height to achieve the same balance. The atmosphere, as a unit of pressure, is defined as being exactly equal to 101,325 pascals, and it was originally intended to represent the average atmospheric pressure at sea level at a latitude of 45 degrees. This unit, while convenient for expressing pressures in a way that relates directly to everyday experience, is not commonly used in precise scientific work, where the pascal or the kilopascal is preferred, nor in meteorology, where the hectopascal or millibar is standard. Nevertheless, the atmosphere remains a useful reference point, and it is often encountered in chemistry and physics, where standard conditions are frequently defined in terms of a pressure of 1 atmosphere and a temperature of 0 degrees Celsius, or, in the case of the more recently adopted standard ambient temperature and pressure, 25 degrees Celsius and 100,000 pascals. The torr, which is named after the Italian physicist and mathematician Evangelista Torricelli, who lived from 1608 to 1647, is another unit of pressure that is closely related to the millimeter of mercury. 1 torr is defined as exactly 1/760th of a standard atmosphere, which makes it approximately equal to 133.322 pascals, and for most practical purposes, 1 torr may be considered to be equivalent to 1 millimeter of mercury, although there is a very slight difference between the two, amounting to less than 1 part in 7 million, which arises from the precise definitions of the respective units and the standardized value of the density of mercury. The story of how barometric pressure came to be understood and measured is one that begins in the early 17th century, in a period when the nature of the atmosphere and the existence of a vacuum were subjects of considerable philosophical and scientific debate. The ancient Greek philosopher Aristotle, who lived from 384 to 322 BC, had asserted that nature abhors a vacuum, a principle that was widely accepted for nearly 2 millennia and that was used to explain various phenomena, including the operation of suction pumps, which were believed to draw water upward by creating a vacuum that the water rushed to fill, rather than by any mechanism involving atmospheric pressure. It was observed by well diggers and pump operators in Italy, however, that suction pumps were unable to raise water above a height of approximately 10 meters, or roughly 34 feet, a limitation that could not be satisfactorily explained by the Aristotelian principle, and this observation attracted the attention of the Italian scientist Galileo Galilei, who, in the later years of his life, discussed the problem with his student and colleague Evangelista Torricelli. Galileo, who lived from 1564 to 1642, suggested that the limitation might be related to the weight of the column of water itself. But it was Torricelli who developed this idea into a coherent theory and devised the experiment that would prove it. In the year 1643, Evangelista Torricelli, working in Florence, Italy, conducted what is now recognized as one of the most important experiments in the history of physics. Torricelli reasoned that if the atmosphere had weight, then it should be able to support a column of liquid in a sealed tube, and that the height of the column would be determined by the balance between the weight of the liquid and the pressure of the atmosphere. He chose to use mercury rather than water for his experiment because mercury is approximately 13.6 times denser than water, which meant that the column of mercury supported by the atmosphere would be only about 1/13.6 the height of a comparable column of water, making the apparatus much more practical and manageable. Torricelli filled a glass tube, which was approximately 1 meter in length and sealed at one end, with mercury, and then inverted the tube and placed the open end in a dish of mercury. When the tube was inverted, some of the mercury flowed out into the dish, but a column of mercury approximately 760 millimeters in height remained standing in the tube. Supported by the pressure of the atmosphere acting on the surface of the mercury in the dish. The space above the mercury in the sealed end of the tube was devoid of air, and it constituted what is now known as a Torricellian vacuum, which was one of the first artificially created vacuums in the history of science. Torricelli observed that the height of the mercury column varied slightly from day to day, and he correctly attributed these variations to changes in the pressure of the atmosphere, thereby establishing the fundamental principle of the barometer as an instrument for measuring atmospheric pressure. In a letter dated June 11, 1644, addressed to his friend Michelangelo Ricci, Torricelli wrote that the purpose of his experiment was not merely to produce a vacuum, but to make an instrument that would show the changes of the air, which is at times heavier and thicker, and at times lighter and more subtle, and this statement is widely regarded as the founding declaration of the science of barometry. The significance of Torricelli's experiment was recognized relatively quickly by the scientific community of the time, and it prompted a number of further investigations, the most famous of which was conducted by the French mathematician, physicist, and philosopher Blaise Pascal. Pascal, who was born on June 19, 1623, in Clermont-Ferrand, France, and who died on August 19, 1662, in Paris, was a prodigious intellect who made fundamental contributions to mathematics, physics, philosophy, and theology, and his work on atmospheric pressure represents one of the most elegant demonstrations of the scientific method in the early modern period. Pascal reasoned that if the mercury in Torricelli's tube was indeed being supported by the weight of the atmosphere, then the height of the mercury column should decrease at higher altitudes, where there was less atmosphere above the barometer, and therefore less weight pressing down on the mercury in the dish. To test this hypothesis, Pascal arranged for an experiment to be carried out on the Puy de Dôme, a mountain in the Auvergne region of central France that rises to an elevation of approximately 1,465 meters above sea level. The experiment was conducted on September 19, 1648, by Pascal's brother-in-law, Florent Purrier, because Pascal himself was in poor health and was unable to make the climb. Purrier, following Pascal's detailed instructions, set up 2 mercury barometers at the base of the mountain in the garden of the Minim Fathers Monastery in Clermont-Ferrand, at an altitude of approximately 400 meters above sea level. He recorded the height of the mercury column in both barometers, which stood at approximately 711 millimeters of mercury, and then left one barometer at the base with a monk who was instructed to observe it throughout the day, while he carried the other barometer to the summit of the Puy de Dôme. Upon reaching the summit, Purrier set up the barometer and observed that the mercury column stood at approximately 627 millimeters, which was approximately 84 millimeters, or roughly 3 inches, lower than it had been at the base of the mountain. This result was precisely what Pascal had predicted, and it provided compelling evidence that the atmosphere had a finite weight that decreased with altitude, thereby supporting Torricelli's hypothesis and refuting the Aristotelian doctrine that nature abhors a vacuum. When Purrier descended the mountain and checked the barometer that had been left at the base, he found that its reading had not changed significantly during the course of the day, which confirmed that the difference in readings between the 2 locations was due to the difference in altitude and not to some other factor. Pascal published the results of this experiment in his work entitled Recit de la Grande Expérience de l'Équilibre de Liqueurs, which translates to Account of the Great Experiment on the Equilibrium of Liquids, and this publication, which appeared in 1648, is considered to be one of the landmark documents in the history of physics. The experiment on the Puy de Dôme not only established the principle that atmospheric pressure decreases with altitude, but it also demonstrated a method by which altitude could be estimated from barometric readings, a technique that would later become of great importance in aviation and mountaineering. Following the Puy de Dôme experiment, Pascal conducted further investigations into the nature of pressure in fluids, and he formulated what is now known as Pascal's principle, which states that a change in pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and to the walls of the containing vessel. This principle, which is fundamental to the science of hydraulics, was published posthumously in Pascal's Traité de l'équilibre de liqueurs et de la pesanteur de la masse de l'air, which appeared in 1663, the year after his death, and which contains a comprehensive treatment of both hydrostatics and the physics of the atmosphere. The mercury barometer, as invented by Torricelli and validated by Pascal, remained the primary instrument for measuring atmospheric pressure for more than 2 centuries, and during that time, a number of refinements and improvements were made to its design. The Fortin barometer, which was developed by the French instrument maker Jean-Nicolas Fortin in the early 19th century, incorporated a number of improvements. including a cistern with an adjustable bottom that allowed the level of mercury in the dish to be set to a reference mark before each reading, thereby eliminating a significant source of error that was present in earlier designs. The Kew pattern barometer, which was developed at the Kew Observatory in England in the middle of the 19th century, used a fixed cistern and a scale that was corrected for the variation in the level of mercury in the cistern as the atmospheric pressure changed, providing a simpler and more robust instrument that was suitable for use in weather stations and other locations where regular and reliable readings were required. The accuracy of mercury barometers depends upon a number of factors, including the purity of the mercury, the uniformity of the bore of the glass tube, the temperature of the instrument, and the local value of gravitational acceleration, all of which must be taken into account when making precise measurements. The density of mercury varies with temperature, decreasing by approximately 0.0182% for each degree Celsius increase in temperature, and for this reason, barometric readings are typically corrected to a standard temperature of 0 degrees Celsius before they are reported or compared. Similarly, the local value of gravitational acceleration, which varies with latitude and altitude, affects the relationship between the height of the mercury column and the atmospheric pressure, and corrections for this variation are applied in precise work. The process of reading a mercury barometer with accuracy requires careful attention to several details. The observer must ensure that the instrument is perfectly vertical, that the mercury is free from air bubbles and oxidation, that the meniscus of the mercury is properly illuminated and observed at eye level, and that the vernier scale, if one is present, is read correctly. The meniscus of mercury in a glass tube is convex, meaning that it curves upward at the center, and the standard practice is to read the height of the mercury at the top of the meniscus, which is the point of maximum height. These procedures, which may seem tedious and excessively detailed, are necessary to achieve the level of accuracy that is required for scientific and meteorological purposes, where differences of a fraction of a millimeter can be significant. The establishment of networks of barometric observations was one of the earliest and most important developments in the history of meteorology. In the 17th century, the Grand Duke Ferdinand II of Tuscany, who was a patron of science and a member of the Medici family, established a network of meteorological stations across Italy that recorded barometric pressure, temperature, and other weather variables on a regular basis. This network, which operated from approximately 1654 to 1667, is considered to be the first organized meteorological observation network in history, and the data that it collected provided some of the earliest evidence that weather systems moved across the surface of the Earth in a systematic and potentially predictable manner. In the 18th century, the development of barometric observation networks expanded significantly, with weather stations being established across Europe and in the colonies of the European powers. The Societas Meteorologica Palatina, which was founded in Mannheim, Germany, in 1780, operated a network of 39 meteorological stations across Europe. all of which used standardized instruments and observation procedures, and this network represented a significant advance in the systematic collection of meteorological data. The data collected by these early networks laid the groundwork for the development of synoptic meteorology, which is the branch of meteorology that deals with the analysis and forecasting of weather through the use of simultaneous observations from multiple locations. The relationship between barometric pressure and weather was recognized from the very earliest days of barometry. Torricelli himself had noted that the height of the mercury column varied from day to day, and he had attributed these variations to changes in the atmosphere. By the late 17th century, it had become well established that falling barometric pressure was generally associated with approaching storms and unsettled weather, while rising barometric pressure was associated with clearing skies and fair weather. This empirical relationship, which was observed and documented by numerous scientists and weather enthusiasts over the course of several centuries, formed the basis of weather forecasting long before the underlying physical mechanisms were fully understood. The word barometer itself is derived from the Greek words baros, meaning weight, and metron, meaning measure, and it was first used in English in the mid-17th century to describe the instrument invented by Torricelli. The term was coined by the Irish scientist Robert Boyle, who, along with his contemporaries Robert Hooke and Edmund Halley, made significant contributions to the early development of barometry and the understanding of atmospheric pressure. Boyle, who is perhaps best known for Boyle's law, which describes the inverse relationship between the pressure and volume of a gas at constant temperature, published extensively on the subject of atmospheric pressure and the design of barometers, and his work helped to establish barometry as a rigorous and quantitative branch of natural philosophy. The mercury barometer, despite its elegance and accuracy, has certain practical limitations that have led to the development of alternative types of barometers over the centuries. Mercury is a toxic substance, and the handling and disposal of mercury barometers requires careful attention to safety procedures. Mercury barometers are also relatively fragile and sensitive to being moved or jostled, which makes them unsuitable for use in certain environments, such as on board ships or in field conditions. Furthermore, the reading of a mercury barometer requires a certain degree of skill and attention, and the instrument cannot easily be adapted for automatic or continuous recording of pressure data. These limitations provided the motivation for the development of the aneroid barometer, which was invented in the 19th century and which uses a sealed, partially evacuated metal capsule rather than a column of mercury to sense changes in atmospheric pressure. The aneroid barometer, which will be discussed in considerably greater detail in the following section of this presentation, represented a significant advance in the practical measurement of barometric pressure, as it was portable, robust, and could be adapted for use as a recording instrument, and it eventually supplanted the mercury barometer in most applications outside of the most precise scientific work. The measurement of barometric pressure, which began with Torricelli's simple experiment involving a glass tube and a dish of mercury, has evolved over the course of nearly 4 centuries into a sophisticated and highly accurate endeavor that employs a wide variety of instruments and techniques. From the mercury barometers that still stand in the hallways of venerable scientific institutions to the microelectromechanical sensors that are embedded in modern smartphones, the fundamental principle remains the same. The atmosphere has weight, and that weight can be measured. The precise and continuous monitoring of barometric pressure is essential to modern meteorology, aviation, and numerous other fields, and the instruments and methods that are used to carry out this monitoring are the product of centuries of scientific inquiry and technological development. The standard atmosphere, which is a reference model of the Earth's atmosphere that specifies the variation of pressure, temperature, density, and other properties with altitude, was first defined by the International Commission for Air Navigation in 1924, and it has been revised and updated several times since then, most recently in 1976, when the U.S. Standard Atmosphere was published. According to this model, the pressure at sea level is 101,325 pascals, the temperature is 15 degrees Celsius, and the density of air is approximately 1.225 kilograms per cubic meter. The pressure decreases approximately exponentially with altitude, falling to approximately 89,875 pascals at an altitude of 1,000 meters, 54,019 pascals at 5,000 meters, 26,436 pascals at 10,000 meters, and 1,109 pascals at 30,000 meters, or approximately 30 kilometers above sea level. These values, while they represent idealized conditions that may not correspond exactly to the actual state of the atmosphere at any given time or place, provide a useful baseline for calculations and comparisons. And they are widely used in aviation, engineering, and atmospheric science. The decrease in pressure with altitude is not strictly exponential, because the temperature of the atmosphere also varies with altitude in a complex manner, but the exponential approximation is sufficiently accurate for many purposes, and it provides a convenient mathematical framework for understanding and predicting the variation of pressure with height. The measurement of barometric pressure, as tedious and unremarkable as it may seem to the casual observer, is in fact one of the most fundamental and important measurements in all of the physical sciences. It is through the measurement of barometric pressure that we are able to track and predict the movement of weather systems across the surface of the Earth, to determine the altitude of aircraft and mountaineers, to calibrate scientific instruments and industrial processes, and to understand the structure and behavior of the atmosphere in which we live. The instruments and methods that have been developed for this purpose, from Torricelli's simple glass tube to the sophisticated electronic sensors of the modern era, represent a remarkable achievement of human ingenuity and perseverance, and their story is one that deserves to be told, even if, as is hoped, the telling of it proves to be sufficiently monotonous to induce a state of restful sleep. The aneroid barometer, which derives its name from the Greek word aneros, meaning without liquid, was first conceived and developed in the first half of the 19th century as an alternative to the mercury barometer, and it represented a significant departure from the liquid-based measurement principle that had been established by Torricelli nearly 200 years earlier. The fundamental sensing element of an aneroid barometer is a small, sealed capsule, typically made of a copper beryllium alloy or a similar elastic metal, from which most of the air has been evacuated, creating a partial vacuum within the capsule. As the atmospheric pressure increases, the external force acting on the capsule causes it to compress slightly, and as the atmospheric pressure decreases, the capsule expands. And these minute mechanical deflections are amplified through a system of levers and springs and communicated to a pointer that moves across a calibrated dial. The invention of the aneroid barometer is generally attributed to the French scientist Lucien Vitti, who obtained a patent for his design in 1844, although it should be noted that the concept of using a sealed, evacuated container to measure atmospheric pressure had been proposed earlier by the German mathematician and philosopher Gottfried Wilhelm Leibniz in 1702. Vitti's design, however, was the first to be commercially viable and practically useful, and it incorporated a number of engineering innovations that made the instrument sufficiently sensitive and reliable for meteorological purposes. The aneroid capsule in Vitti's barometer was a corrugated disc, approximately 50 to 60 millimeters in diameter, with the corrugation serving to increase the flexibility of the capsule and to allow it to deform in a more controlled and predictable manner in response to changes in pressure. The mechanical linkage that connects the aneroid capsule to the indicating pointer is a critical component of the instrument, and its design has been the subject of considerable engineering effort over the years. In a typical aneroid barometer, the deflection of the capsule is transmitted through a series of levers that amplify the motion by a factor of approximately 200 to 300, so that a capsule deflection of perhaps 0.05 millimeters, which corresponds to a pressure change of approximately 1 millibar, is translated into a pointer movement of approximately 10 to 15 millimeters on the dial. The levers are typically made of a lightweight but rigid material, such as brass or steel, and they are mounted on low-friction pivot points to minimize the mechanical losses that would otherwise reduce the sensitivity of the instrument. A compensating element, usually in the form of a bimetallic strip or a temperature-compensating spring, is incorporated into the linkage to counteract the effects of temperature changes on the dimensions of the capsule and the mechanical components. Without such compensation, a change in temperature would cause the capsule to expand or contract independently of any change in atmospheric pressure, leading to erroneous readings. The temperature coefficient of an uncompensated aneroid barometer can be as large as 0.3 to 0.5 millibars per degree Celsius, which is sufficient to introduce significant errors in environments where the temperature varies by more than a few degrees, and for this reason, temperature compensation is considered to be an essential feature of any aneroid barometer that is intended for serious meteorological use. The accuracy of a well-made aneroid barometer is typically in the range of 0.5 to 1.0 millibars, which, while not equal to the accuracy of a precision mercury barometer, which can achieve accuracies of 0.1 millibars or better, is more than adequate for most meteorological and general-purpose applications. The resolution of an aneroid barometer, which is the smallest change in pressure that can be detected, is typically about 0.1 to 0.2 millibars, and the instrument responds to pressure changes within a few seconds, making it suitable for tracking the relatively slow variations in atmospheric pressure that are associated with weather systems. The aneroid barometer, in the form of the familiar round dial instrument that is found in homes, offices, and ships around the world, became enormously popular in the latter half of the 19th century, and it was manufactured in vast quantities by firms in England, France, Germany, and the United States. The dials of these instruments were typically marked with both a pressure scale, in inches of mercury or millibars, and a series of weather indications, such as fair, change, rain, and stormy, which were arranged around the dial in positions corresponding to the barometric pressures that were empirically associated with those weather conditions. While these weather indications were necessarily approximate and could not account for the many factors other than barometric pressure that influence the weather, they provided a useful general guide that was appreciated by the general public and by mariners, for whom the barometer was an indispensable navigational instrument. The barograph is a specialized form of aneroid barometer that incorporates a recording mechanism, allowing the continuous variation of atmospheric pressure to be recorded on a chart over a period of time, typically 1 week. The barograph was developed in the latter part of the 19th century, and it quickly became a standard instrument in weather stations, observatories, and other locations where a permanent record of pressure variations was desired. The recording mechanism of a barograph consists of a pen or stylus that is attached to the aneroid capsule linkage and that traces a line on a chart that is wrapped around a slowly rotating drum, which is driven by a clockwork mechanism. The chart of a barograph, which is known as a barogram, is typically divided into horizontal lines representing pressure values, usually at intervals of 2 or 5 millibars, and vertical lines representing time, usually at intervals of 2 or 6 hours. The drum of the barograph completes 1 revolution in 7 days, and the chart is replaced weekly, providing a continuous record of the atmospheric pressure that can be examined for trends, fluctuations, and other features that are of interest to meteorologists and other observers. The barograph is particularly useful for identifying the passage of weather fronts, the approach of storms, and the diurnal variation of atmospheric pressure, which is irregular. Twice-daily oscillation in pressure that is caused by the heating and cooling of the atmosphere by the sun, and that has an amplitude of approximately 1 to 2 millibars at most locations. The development of electronic pressure sensors in the latter half of the 20th century brought about a revolution in the measurement of barometric pressure that was comparable in significance to the introduction of the aneroid barometer a century earlier. Electronic pressure sensors, which convert the mechanical deflection caused by pressure changes into an electrical signal, offer a number of advantages over mechanical barometers, including higher accuracy, greater resolution, faster response times, and the ability to interface directly with computers and data logging systems. The earliest electronic pressure sensors used strain gauges, which are thin metallic or semiconducting elements whose electrical resistance changes when they are deformed. And these sensors were capable of measuring pressure with an accuracy of approximately 0.1 to 0.5 millibars. The development of microelectromechanical systems, commonly known as MEMS, in the 1990s and 2000s led to the creation of pressure sensors that were not only highly accurate, but also extraordinarily small and inexpensive. A MEMS pressure sensor consists of a tiny diaphragm, typically made of silicon, that is fabricated using semiconductor manufacturing techniques and that deflects in response to changes in pressure. The deflection of the diaphragm is measured using piezoresistive elements that are integrated into the silicon structure, or by measuring the change in capacitance between the diaphragm and a fixed electrode. MEMS pressure sensors can be manufactured in very large quantities at very low cost, and they are now found in a wide variety of consumer electronics devices, including smartphones, tablets, and fitness trackers, where they are used for altitude determination, indoor navigation, and weather monitoring. The Bosch BMP-280, which is one of the most widely used MEMS barometric pressure sensors, measures approximately 2.0 by 2.5 by 0.95 millimeters, which is smaller than a grain of rice. And it is capable of measuring pressure with an absolute accuracy of plus or minus 1 hectopascal and a resolution of 0.16 pascals, which corresponds to an altitude resolution of approximately 0.01 meters. The sensor consumes only 2.7 microamperes of current in its lowest power mode, which allows it to operate for years on a small battery, and it communicates with other electronic components through a standard digital interface. The successor to this sensor, the BMP-390, offers even greater accuracy, with a relative accuracy of plus or minus 0.03 hectopascals and a noise level of only 0.02 pascals, which represents a remarkable level of performance for a device that costs less than $1 in large quantities. The calibration of barometers, whether mercury, aneroid, or electronic, is a process that is essential to ensuring the accuracy and reliability of the measurements that they produce. Calibration involves comparing the readings of the barometer under test with the readings of a reference standard of known accuracy and adjusting or correcting the instrument as necessary to bring its readings into agreement with the standard. The highest level reference standards for barometric pressure are maintained by national metrology institutes, such as the National Institute of Standards and Technology in the United States, the Physikalisch-Technische Bundesanstalt in Germany, and the National Physical Laboratory in the United Kingdom, and these standards are traceable to the fundamental definition of the Pascal through a chain of comparisons and calibrations. The calibration of a mercury barometer involves verifying the accuracy of the scale, the alignment of the instrument, the purity of the mercury, and the corrections for temperature and gravity that are applied to the readings. The calibration of an aneroid barometer involves comparing its readings with those of a reference mercury barometer or a calibrated electronic sensor over a range of pressures that spans the expected operating range of the instrument, and adjusting the mechanical linkage or applying correction factors as necessary. The calibration of an electronic pressure sensor involves exposing it to a series of known pressures generated by a precision pressure controller and recording the electrical output of the sensor at each pressure, from which a calibration curve is derived that relates the electrical output to the true pressure. The frequency of calibration depends upon the application and the required level of accuracy. For weather stations that are part of national or international observation networks, calibration is typically performed at intervals of 1 to 2 years, and the instruments are required to meet specified accuracy standards, such as plus or minus 0.3 hectopascals for mercury barometers and plus or minus 0.5 hectopascals for aneroid barometers. For scientific research applications, where higher accuracy may be required, calibration may be performed more frequently, and additional corrections may be applied for factors such as the thermal expansion of the instrument components and the local value of gravitational acceleration. The establishment and operation of weather station networks for the purpose of monitoring barometric pressure and other meteorological variables is a large-scale undertaking that involves thousands of surface stations, hundreds of upper-air sounding stations, and a global telecommunications infrastructure for the collection and distribution of observational data. The World Meteorological Organization, which is a specialized agency of the United Nations with a membership of 193 states and territories, coordinates the international exchange of meteorological data through its World Weather Watch program, which was established in 1963 and which provides the framework for the global observation, data processing, and telecommunications systems that support weather forecasting and climate monitoring. Surface weather stations, of which there are approximately 11,000 in the global network maintained by the World Meteorological Organization, measure barometric pressure along with temperature, humidity, wind speed, and direction, precipitation, cloud cover, and visibility, and they report these observations at regular intervals, typically every 3 or 6 hours, using a standardized format and coding system. The barometric pressure reported by surface stations is typically reduced to sea level, which means that the observed station pressure is adjusted to the value that would be expected if the station were located at sea level, by adding a correction that accounts for the altitude of the station and the temperature of the air column between the station and sea level. This reduction to sea level is necessary to allow meaningful comparisons of pressure between stations at different altitudes, and it is the sea level pressure that is plotted on weather maps and used in weather forecasting. The measurement of barometric pressure in the upper atmosphere is accomplished primarily through the use of radiosondes, which are small, expendable instrument packages that are carried aloft by helium, or hydrogen-filled weather balloons. A radiosonde measures pressure, temperature, and humidity as it ascends through the atmosphere, and it transmits the data by radio to a ground receiving station. The balloon typically ascends to an altitude of approximately 30 to 35 kilometers, which corresponds to a pressure of approximately 10 to 5 hectopascals, before the balloon bursts and the radiosonde descends to the ground on a small parachute. Radiosonde observations are made twice daily, at midnight and 12 o'clock Coordinated Universal Time, at approximately 900 stations around the world. And the data that they provide are essential for initializing the numerical weather prediction models that are used to produce weather forecasts. The pressure sensor in a modern radiosonde is typically a silicon capacitive sensor, similar in principle to the MEMS sensors used in consumer electronics, but designed to operate over the much wider pressure range encountered in the upper atmosphere, from approximately 1,050 hectopascals at the surface to less than 5 hectopascals at the burst altitude. The accuracy of these sensors is typically better than plus or minus 1 hectopascal, and the data are transmitted to the ground station at intervals of 1 to 2 seconds, providing a detailed vertical profile of pressure, temperature, and humidity through the depth of the atmosphere. The concept of pressure altitude, which is the altitude in the standard atmosphere corresponding to a given barometric pressure, is of fundamental importance in aviation, where it is used to maintain vertical separation between aircraft and to ensure safe clearance above terrain and obstacles. The altimeter in an aircraft is essentially a calibrated aneroid barometer that indicates altitude rather than pressure, and it is set to a reference pressure before each flight so that the indicated altitude corresponds to the actual altitude above a known reference level. When an aircraft is flying below an altitude of approximately 18,000 feet, or 5,486 meters in the United States, or below the transition altitude in other countries, the altimeter is set to the local sea level pressure, which is provided by air traffic control and which is known as the QNH setting. This setting ensures that the altimeter indicates the aircraft's altitude above sea level, which is useful for terrain clearance and for landing at airports whose elevations are known. When an aircraft is flying above the transition altitude, which is 18,000 feet in the United States, the altimeter is set to the standard pressure of 1,013.25 hectopascals, or 29.92 inches of mercury, and the indicated altitude is referred to as a flight level. This convention ensures that all aircraft flying at high altitudes are using the same pressure reference, which is essential for maintaining vertical separation. Even though the indicated altitude may not correspond exactly to the true altitude above sea level. The relationship between pressure and altitude is described by the hypsometric equation, which states that the thickness of an atmospheric layer is proportional to the mean virtual temperature of the layer and the natural logarithm of the ratio of the pressures at the bottom and top of the layer. In the standard atmosphere, where the temperature decreases linearly with altitude at a rate of 6.5 degrees Celsius per kilometer in the troposphere, The pressure at an altitude h in meters can be approximated by the formula P equals P0 times the quantity 1 minus h divided by 44,330 raised to the power of 5.255, where P0 is the sea level pressure of 101,325 pascals. This formula, while approximate, provides a reasonably accurate estimate of the pressure at any altitude in the troposphere, and it is used in many practical applications, including the calibration of altimeters and the reduction of barometric observations to sea level. The measurement of barometric pressure from space has become an increasingly important component of the global atmospheric observation system in recent decades. Satellite-based instruments, such as the Atmospheric Infrared Sounder on NASA's Aqua satellite and the Infrared Atmospheric Sounding Interferometer on the European MEDOP satellites, can estimate atmospheric pressure indirectly by measuring the infrared radiation emitted by the atmosphere and using radiative transfer models to infer the temperature and pressure profiles. While these satellite-based measurements are not as accurate as direct measurements from radiosondes or surface stations, they provide global coverage, including over the oceans and other remote areas where conventional observations are sparse. And they're an essential input to the numerical weather prediction models that are used to produce weather forecasts. The history of the aneroid barometer in maritime use is particularly noteworthy, as the instrument proved to be far more practical for use at sea than the mercury barometer, which was susceptible to the rolling and pitching of the ship, and which required careful mounting and observation procedures to obtain reliable readings. The aneroid barometer could be mounted on a bulkhead in any orientation and read at a glance, and it was not affected by the motion of the vessel, making it an ideal instrument for use by sailors and navigators. The British Admiralty adopted the aneroid barometer for use in the Royal Navy in the latter part of the 19th century, and it quickly became a standard instrument on both military and commercial vessels. The importance of the barometer to maritime safety was recognized by the International Convention for the Safety of Life at Sea, which requires all vessels of a certain size to carry a barometer and to maintain a log of barometric observations. The development of the precision aneroid barometer, which is a high-quality aneroid instrument that is designed to achieve an accuracy comparable to that of a mercury barometer, has been the subject of considerable engineering effort. Precision aneroid barometers typically use multiple aneroid capsules stacked together to increase the total deflection and sensitivity of the instrument, and they incorporate sophisticated temperature compensation systems and high-quality mechanical linkages. The Pollen aneroid barometer, which was developed in France in the early 20th century, used a stack of 7 or more aneroid capsules and achieved an accuracy of approximately 0.3 millibars, which was comparable to the accuracy of a good mercury barometer. Modern precision aneroid barometers, which use electronic readout systems rather than mechanical linkages, can achieve accuracies of 0.1 millibars or better, and they're used as transfer standards for the calibration of other barometric instruments. The digital barometer, which combines an electronic pressure sensor with a microprocessor and a digital display, has largely replaced the traditional aneroid barometer in both professional and consumer applications. Digital barometers offer a number of advantages over their mechanical predecessors, including higher accuracy and resolution, automatic temperature compensation, the ability to store and display historical data, and the ability to calculate and display derived quantities, such as the pressure tendency and the altitude. Many digital barometers also include additional sensors for temperature and humidity, and they can be connected to computers or wireless networks for remote monitoring and data logging. The integration of MEMS barometric pressure sensors into smartphones and other portable electronic devices has created a vast, distributed network of pressure sensing instruments that has the potential to revolutionize the collection of atmospheric pressure data. Research projects such as the PressureNet initiative, which was launched in 2012, have explored the possibility of using the barometric sensors in smartphones to create a dense network of atmospheric pressure observations that could supplement the data from conventional weather stations and improve the accuracy of weather forecasts, particularly for small-scale and short-lived weather phenomena such as thunderstorms and tornadoes. While there are significant challenges associated with the use of smartphone pressure data, including issues of sensor quality, calibration, and the effects of indoor environments on the readings, the sheer number of potential observation points, which numbers in the billions, makes this an area of active research and development. The use of unmanned aerial vehicles, commonly known as drones, for atmospheric pressure measurement has also emerged as a promising area of research in recent years. Drones equipped with barometric pressure sensors and other meteorological instruments can be deployed to measure the vertical profile of pressure and temperature in the lower atmosphere, providing data that complement the observations from radiosondes and surface stations. Drones have the advantage of being able to operate at low altitudes and in specific locations where radiosondes do not provide adequate coverage, and they can be deployed on demand in response to specific weather events or research needs. The Global Navigation Satellite System, which includes the American GPS, the Russian GLONASS, the European Galileo, and the Chinese Beidou systems, has also been utilized for atmospheric pressure measurement through a technique known as GNSS radio occultation. In this technique, the signals transmitted by navigation satellites are received by a satellite in low Earth orbit as they pass through the Earth's atmosphere, and the bending and delay of the signals caused by the atmospheric refraction are used to derive profiles of pressure, temperature, and humidity. This technique, which was first demonstrated by the GPS/MED experiment in 1995, provides pressure measurements with an accuracy of approximately 0.1 to 1 hectopascal in the upper troposphere and stratosphere, and it has become an important source of data for weather forecasting and climate research. The network of instruments and systems that are used to measure barometric pressure on a global scale is thus extraordinarily extensive and diverse, encompassing mercury barometers that have been in continuous operation for more than a century, modern electronic sensors that can be held in the palm of a hand, weather balloons that ascend to the edge of space, and satellites that orbit the Earth at altitudes of hundreds or thousands of kilometers. The data from all of these sources are collected, quality controlled, and assimilated into numerical weather prediction models, which use the laws of physics to simulate the behavior of the atmosphere and to produce forecasts of future weather conditions. The measurement of barometric pressure, which began with a simple glass tube and a dish of mercury in a laboratory in Florence in 1643, has grown into a global enterprise of enormous complexity and importance, and it continues to evolve as new technologies and techniques are developed. The relationship between barometric pressure and the weather that is experienced at the surface of the Earth is one that has been recognized and studied for centuries, and it forms one of the cornerstones of modern meteorological practice. The fundamental principle upon which this relationship is based is that variations in atmospheric pressure at the surface are associated with the large-scale movement and redistribution of air masses in the atmosphere, and these movements, in turn, determine the patterns of wind, cloud formation, precipitation, and temperature that constitute what we commonly refer to as the weather. The systematic observation and analysis of barometric pressure patterns across a wide area, which is the essence of synoptic meteorology, allows forecasters to identify the location and intensity of weather systems and to predict their future movement and development with a degree of accuracy that would have seemed miraculous to the early pioneers of barometry. A region of relatively high atmospheric pressure at the surface is known as an anticyclone, or simply as a high-pressure system, and it is typically associated with fair weather, clear skies, light winds, and stable atmospheric conditions. In an anticyclone, the air is subsiding or sinking from higher altitudes toward the surface, and this downward motion causes the air to warm adiabatically, which inhibits the formation of clouds and precipitation. The wind in an anticyclone circulates in a clockwise direction in the northern hemisphere and in a counterclockwise direction in the southern hemisphere, owing to the Coriolis effect, which is the deflection of moving objects caused by the rotation of the Earth. Anticyclones can persist for days or even weeks, particularly in certain favored locations, and they are generally associated with dry, settled weather, although in winter they can also be associated with fog and frost, due to the clear skies and light winds that allow the surface to cool rapidly by radiative heat loss. A region of relatively low atmospheric pressure at the surface is known as a cyclone, or simply as a low-pressure system, and it is typically associated with unsettled weather, cloud cover, precipitation, and stronger winds. In a cyclone, the air is rising from the surface toward higher altitudes, and this upward motion causes the air to cool adiabatically, which promotes the condensation of water vapor and the formation of clouds and precipitation. The wind in a cyclone circulates in a counterclockwise direction in the northern hemisphere and in a clockwise direction in the southern hemisphere, and the intensity of the wind is generally greater in cyclones than in anticyclones, because the pressure gradients associated with cyclones are typically steeper. Cyclones are the primary mechanism by which energy and moisture are transported from the tropics toward the poles, and they play a crucial role in maintaining the overall energy balance of the atmosphere. The pressure at the center of a typical mid-latitude cyclone ranges from approximately 970 to 1,000 hectopascals, while the pressure at the center of a typical anticyclone ranges from approximately 1,020 to 1,040 hectopascals. In extreme cases, the pressure at the center of an intense cyclone can fall much lower. The lowest sea level pressure ever recorded was 870 hectopascals, which was measured in the eye of Typhoon Tip on October 12, 1979, in the western Pacific Ocean. At the other extreme, the highest sea level pressure ever recorded was 1,083.8 hectopascals, which was measured at Agata, Siberia, on December 31, 1968, during an exceptionally cold and stable winter anticyclone. The range of sea level pressure observed on Earth thus extends over approximately 214 hectopascals, or about 21% of the mean sea level pressure, although variations of this magnitude are extremely rare. And the vast majority of sea level pressure observations fall within the range of approximately 960 to 1,050 hectopascals. The representation of barometric pressure on a weather map is accomplished through the use of isobars, which are lines drawn on the map connecting points of equal sea level pressure. Isobars are typically drawn at intervals of 4 hectopascals, or 4 millibars, and they provide a visual depiction of the horizontal distribution of pressure across the mapped area. The pattern of isobars on a weather map reveals the location and extent of high-pressure and low-pressure systems, the strength of the pressure gradient, and the direction and approximate speed of the geostrophic wind, which is the wind that would blow parallel to the isobars in the absence of friction. The pressure gradient, which is the rate of change of pressure with horizontal distance, is the primary driving force behind the wind. Air tends to flow from regions of higher pressure toward regions of lower pressure, in much the same way that water flows downhill, and the steeper the pressure gradient, the stronger the resulting wind. On a weather map, a steep pressure gradient is indicated by closely spaced isobars, while a gentle pressure gradient is indicated by widely spaced isobars. The relationship between the pressure gradient and the wind speed is modified by the Coriolis effect and by friction, both of which act to deflect or slow the air as it moves from high to low pressure. And the resulting wind pattern is a complex balance between the pressure gradient force, the Coriolis force, and frictional forces. The geostrophic wind, which is the theoretical wind that results from a balance between the pressure gradient force and the Coriolis force in the absence of friction, blows parallel to the isobars, with low pressure to the left of the wind direction in the northern hemisphere and to the right in the southern hemisphere. This relationship, which is known as Buys-Ballott's law, after the Dutch meteorologist Christophorus Buys-Ballot, who formulated it in 1857, provides a useful rule of thumb for estimating the wind direction from a weather map. Although the actual surface wind is typically deflected somewhat toward lower pressure, at an angle of approximately 10 to 30 degrees from the isobars due to the effect of friction with the surface. The analysis of barometric pressure patterns is also fundamental to the identification and tracking of weather fronts, which are the boundaries between air masses of different temperature and humidity characteristics. A cold front, which is the leading edge of an advancing mass of cold air, is typically associated with a trough of low pressure and a sharp change in wind direction, and it is often accompanied by a band of precipitation that may be heavy but relatively brief. A warm front, which is the leading edge of an advancing mass of warm air, is also associated with a trough of low pressure, but the change in wind direction is more gradual, and the precipitation is typically more widespread but lighter in intensity. The location of fronts on a weather map is determined in part by the analysis of the pressure field, as fronts are generally found in regions where the isobars exhibit a sharp change in direction or spacing. The use of barometric pressure in weather forecasting has been greatly enhanced by the development of numerical weather prediction, which is the simulation of the atmosphere using mathematical models that are solved on high-performance computers. The first operational numerical weather prediction was performed by the Royal Swedish Air Force Weather Service in 1954, using a model developed by the Swedish meteorologist Carl Gustav Rossby and his colleagues, and since then, numerical weather prediction has become the primary tool of weather forecasting agencies around the world. Modern numerical weather prediction models, such as the Integrated Forecast System operated by the European Centre for Medium-Range Weather Forecasts and the Global Forecast System operated by the National Centers for Environmental Prediction in the United States, use millions of observations of barometric pressure, temperature, humidity, and wind from surface stations, radiosondes, satellites, aircraft, and other sources to initialize a three-dimensional representation of the atmosphere, and they then integrate the equations of motion forward in time to predict the future state of the atmosphere. The accuracy of numerical weather prediction has improved steadily since its inception, owing to advances in observational systems, computational power, and the physical understanding of the atmosphere. And modern forecasts are skillful out to approximately 7 to 10 days for large-scale weather patterns and approximately 3 to 5 days for specific weather events, such as precipitation and severe weather. The barometric pressure field is one of the most accurately predicted variables in numerical weather prediction, because the large-scale pressure patterns are governed primarily by well-understood dynamical processes, and the density and accuracy of surface pressure observations provide a strong constraint on the initial state of the model. The relationship between barometric pressure and human health is a subject that has been discussed and debated for centuries, and it continues to be a topic of both scientific research and popular interest. Many people claim to be able to sense changes in barometric pressure through physical symptoms, such as joint pain, headaches, and changes in mood, and there is a long tradition in folk medicine of attributing various ailments to changes in the weather. The scientific evidence for a direct causal link between barometric pressure and health is mixed, however, And while some studies have found statistically significant correlations between pressure changes and certain health outcomes, the mechanisms by which pressure changes might affect the human body are not well understood, and the observed effects are generally small and inconsistent. One area where there is relatively strong evidence for a relationship between barometric pressure and health is in the domain of joint pain, particularly in individuals suffering from arthritis. Several studies have found that decreases in barometric pressure are associated with increased reports of joint pain, and it has been hypothesized that the reduction in external pressure allows the tissues around the joints to expand slightly, putting pressure on the nerves and causing discomfort. However, other studies have failed to find a consistent relationship, and a systematic review published in the journal BMC Musculoskeletal Disorders in 2014 concluded that the evidence was insufficient to establish a definitive link between barometric pressure and joint pain. The magnitude of the pressure changes associated with normal weather variations is relatively small, amounting to perhaps 2 to 3% of the total atmospheric pressure, and it is unclear whether such small changes could have a significant physiological effect. The relationship between barometric pressure and migraine headaches has also been the subject of considerable research. A study published in the journal Internal Medicine in 2011 found that decreases in barometric pressure were associated with an increased incidence of migraine headaches, with the risk increasing by approximately 6% for each 5 hectopascal decrease in pressure. Other studies have reported similar findings, but the evidence is not conclusive, and it is possible that the observed association is mediated by other weather-related factors, such as temperature changes, humidity, or changes in light levels, rather than by pressure changes per SE. The variation of barometric pressure with altitude is described by the barometric formula, which is a mathematical expression that relates the pressure at a given altitude to the pressure at a reference level, the temperature of the air, and the acceleration due to gravity. In its simplest form, the barometric formula assumes that the atmosphere is composed of an ideal gas at a constant temperature, and it predicts that the pressure decreases exponentially with altitude, with a scale height that is proportional to the temperature and inversely proportional to the molecular weight of the air and the acceleration due to gravity. The scale height of the atmosphere, which is the altitude over which the pressure decreases by a factor of E, which is approximately 2.71828, is approximately 8,500 meters, or 8.5 kilometers, at a temperature of 15 degrees Celsius. This means that for every 8.5 kilometers of altitude gained, the pressure decreases by a factor of approximately 2.718, so that at an altitude of 8.5 kilometers, the pressure is approximately 37% of its sea level value, and at an altitude of 17 kilometers, the pressure is approximately 14% of its sea level value. In reality, the temperature of the atmosphere is not constant, but varies with altitude in a complex manner, and the barometric formula must be modified to account for this variation. But the exponential decrease of pressure with altitude remains a useful and approximately correct description of the actual pressure profile. The standard atmosphere model, which was discussed earlier in this presentation, provides a more detailed and accurate description of the variation of pressure with altitude than the simple barometric formula. By specifying the temperature profile of the atmosphere in a series of layers, each with a constant temperature lapse rate. According to the International Standard Atmosphere, which is defined by the International Civil Aviation Organization, the atmosphere is divided into the troposphere, which extends from the surface to an altitude of 11,000 meters. The tropopause at 11,000 meters, the lower stratosphere, from 11,000 to 20,000 meters, the upper stratosphere, from 20,000 to 32,000 meters, and several additional layers extending to an altitude of 86 kilometers. In the troposphere, the temperature decreases linearly with altitude at a rate of 6.5 degrees Celsius per kilometer, from a sea level temperature of 15 degrees Celsius to a temperature of minus 56.5 degrees Celsius at the tropopause. In the lower stratosphere, from 11,000 to 20,000 meters, the temperature is constant at minus 56.5 degrees Celsius, and in the upper stratosphere, from 20,000 to 32,000 meters, the temperature increases with altitude at a rate of 1 degree Celsius per kilometer. The pressure at each level is calculated by integrating the barometric formula through each layer, using the appropriate temperature profile, and the resulting pressure values are tabulated in the standard atmosphere tables that are used in aviation, engineering, and atmospheric science. The standard atmosphere model is a purely theoretical construct that represents average conditions and that does not correspond exactly to the actual state of the atmosphere at any particular time or place. The actual atmospheric pressure at a given altitude may differ from the standard atmosphere value by several percent or more, depending upon the prevailing meteorological conditions. And these differences are of considerable practical importance in aviation, where the accuracy of pressure-based altitude measurements depends upon the degree to which the actual atmosphere conforms to the standard model. The correction of altimeter readings for non-standard atmospheric conditions is a routine part of aviation operations, and it is accomplished through the use of altimeter setting procedures that were described earlier in this presentation. The barometric tendency, which is the rate of change of barometric pressure over time, is an important meteorological parameter that provides information about the current and expected future weather conditions. The barometric tendency is typically calculated over a 3-hour period and is reported as part of the standard surface weather observation. A falling barometric tendency, meaning that the pressure is decreasing over time, is generally associated with the approach of a low-pressure system or a weather front, and it is often a precursor to deteriorating weather conditions. A rising barometric tendency, meaning that the pressure is increasing over time, is generally associated with the passage of a low-pressure system or front and the approach of a high-pressure system, and it is often a precursor to improving weather conditions. The rate at which the barometric pressure changes can provide additional information about the severity and proximity of approaching weather systems. A rapid decrease in pressure of more than approximately 3 to 4 hectopascals in 3 hours is indicative of the approach of a vigorous cyclone or an intense weather front, and it may be associated with strong winds, heavy precipitation, and other severe weather conditions. A slow, steady decrease in pressure of perhaps 1 to 2 hectopascals over several hours is more typical of the gradual approach of a moderate weather system, and it is usually associated with less severe weather conditions. The diurnal variation of barometric pressure, which is a regular, twice-daily oscillation in pressure that is observed at most locations on Earth, is caused primarily by the absorption of solar radiation by the ozone layer in the stratosphere and by water vapor in the troposphere, which causes the atmosphere to expand during the day and contract at night. The amplitude of the diurnal pressure variation is greatest in the tropics, where it averages approximately 1.5 to 3 hectopascals, and it decreases with increasing latitude, averaging approximately 0.5 to 1 hectopascal at mid-latitudes and becoming very small at high latitudes. The maximum pressure occurs at approximately 10 o'clock and 2200 hours local time, and the minimum pressure occurs at approximately 4 o'clock and 1600 hours local time, giving rise to a semi-diurnal pattern with 2 maxima and 2 minima per day. The concept of the pressure altimeter setting, known as QNH in international aviation terminology, deserves further elaboration, as it is a parameter that is communicated to pilots on a routine basis and that has a direct bearing on the safety of flight operations. The QNH is defined as the atmospheric pressure at sea level, calculated from the observed station pressure by applying corrections for the altitude and temperature of the station, and when this value is set on the altimeter's subscale. The altimeter will indicate the aircraft's altitude above mean sea level. The QNH is updated at regular intervals, typically every 30 minutes to 1 hour, and it is broadcast to pilots through automatic terminal information service recordings, air traffic control communications, and meteorological reports known as METRs, which are issued for airports around the world in a standardized format. Another altimeter setting that is used in aviation is the QFE, which is the atmospheric pressure at the airport reference point, without any correction for altitude. When the QFE is set on the altimeter's subscale, the altimeter will indicate the aircraft's height above the airport, rather than its altitude above sea level. The QFE setting is used in some countries and by some air forces for approach and landing procedures, as it provides a direct indication of the aircraft's height above the runway, but it is not universally adopted, and many countries and aviation authorities prefer the QNH setting for all phases of flight. The effect of non-standard temperature on altimeter accuracy is a matter of considerable practical importance in aviation. When the actual temperature of the atmosphere is lower than the standard atmosphere temperature, the air is denser than assumed, and the actual altitude of the aircraft is lower than the altitude indicated by the altimeter. Conversely, when the actual temperature is higher than the standard atmosphere temperature, the actual altitude is higher than the indicated altitude. This effect can be significant in cold weather, where the error can amount to several hundred feet at moderate altitudes, and it is particularly important when aircraft are flying at low altitudes near terrain or obstacles. Pilots are trained to apply cold temperature corrections to their altimeter readings when operating in cold weather conditions, and procedures for doing so are specified in the aviation regulations and guidance material of most countries. The barometric pressure also plays a role in the phenomenon known as the Bergeron process, which is one of the primary mechanisms by which precipitation is formed in the atmosphere. In this process, which was first described by the Swedish meteorologist Tor Bergeron in 1935, ice crystals in the upper regions of a cloud grow at the expense of supercooled water droplets. Because the saturation vapor pressure over ice is lower than the saturation vapor pressure over liquid water at temperatures below freezing. The ice crystals grow by vapor deposition until they are large enough to fall through the cloud, collecting additional water droplets as they descend, and eventually reaching the surface as rain or snow. The efficiency of this process depends upon the temperature and pressure conditions within the cloud, and the barometric pressure, through its effect on the altitude and temperature of the cloud, plays an indirect but important role in determining the type and amount of precipitation that is produced. The relationship between barometric pressure and the boiling point of water is another aspect of pressure science that has practical implications, particularly for cooking at high altitudes. The boiling point of water, which is 100 degrees Celsius at a pressure of 1 standard atmosphere, decreases as the pressure decreases at a rate of approximately 0.34 degrees Celsius per 100 meters of altitude gain. At an altitude of 2,000 meters, where the pressure is approximately 795 hectopascals, the boiling point of water is approximately 93.3 degrees Celsius, and at an altitude of 5,000 meters, where the pressure is approximately 540 hectopascals, the boiling point is approximately 83.3 degrees Celsius. This reduction in boiling point means that food takes longer to cook at higher altitudes because the water in which it is immersed or by which it is surrounded is at a lower temperature. And this is the reason that cooking instructions for high-altitude locations typically call for longer cooking times or the use of pressure cookers, which raise the boiling point by increasing the pressure inside the cooking vessel. This diurnal variation, while small in amplitude, must be taken into account when analyzing barometric pressure data, particularly in the tropics, where it can be comparable in magnitude to the pressure changes associated with weather systems. In the tropics, the absence of the normal diurnal pressure variation can itself be an indication of approaching severe weather, as the pressure field associated with a tropical cyclone can suppress or distort the diurnal oscillation. The barometric pressure in the eye of a hurricane or typhoon drops far below the normal range, and the passage of such a storm is typically accompanied by extremely rapid pressure changes, with rates of decrease of 10 hectopascals per hour or more being common in the strongest storms. The measurement and analysis of barometric pressure thus provides a wealth of information about the state and behavior of the atmosphere, from the large-scale patterns of high and low pressure that govern the movement of weather systems across the globe, to the subtle diurnal oscillations that reflect the daily heating and cooling of the atmosphere, to the rapid pressure changes that herald the approach of severe weather. The instruments and methods that have been developed for measuring barometric pressure, from Torricelli's mercury tube to the MEMS sensors in modern smartphones, represent centuries of scientific and engineering achievement, and they continue to play an essential role in the observation, analysis, and prediction of the weather. The historical development of meteorology as a scientific discipline is intimately intertwined with the history of barometric pressure measurement, and it is not an exaggeration to say that the invention of the barometer was one of the founding events of meteorological science. Before the barometer, the prediction of weather was based entirely upon the observation of visible phenomena, such as the appearance of the sky, the direction and strength of the wind, the behavior of animals, and the accumulated wisdom of farmers, sailors, and other individuals whose livelihoods depended upon the weather. While these empirical methods were not entirely without merit, they were inherently limited in their scope and accuracy, and they provided no quantitative information about the state of the atmosphere that could be systematically recorded, analyzed, and compared across different locations and times. The invention of the barometer by Torricelli in 1643 and the subsequent demonstration by Pascal that atmospheric pressure decreases with altitude provided the first quantitative tool for probing the state of the atmosphere, and they laid the groundwork for the development of meteorology as an exact science. The 18th century saw a gradual accumulation of barometric observations from scattered locations around the world, and by the early 19th century, enough data had been collected to permit the identification of large-scale patterns in the distribution of atmospheric pressure, including the subtropical high-pressure belts, the subpolar low-pressure troughs, and the seasonal variations in pressure associated with the differential heating of land and ocean. The development of the electric telegraph in the 1830s and 1840s transformed meteorology by making it possible, for the first time, to collect weather observations from widely separated locations in near real time. The first weather maps based on telegraphic observations were produced in the 1850s, and the first public weather forecasts were issued in England by Robert Fitzroy, who served as the first head of the meteorological department of the Board of Trade, which was established in 1854. Fitzroy, who is perhaps better known as the captain of HMS Beagle during Charles Darwin's famous voyage, developed a system of storm warnings based on barometric observations that was credited with saving many lives at sea. Although his forecasting methods were criticized by some scientists of the time as being insufficiently rigorous, the Norwegian meteorologist Wilhelm Bjerknes, who lived from 1862 to 1951, proposed in 1904 that weather forecasting should be treated as a problem in mathematical physics, and that the future state of the atmosphere could, in principle, be calculated from its present state by solving the equations of fluid dynamics and thermodynamics that govern the behavior of the atmosphere. This idea, which is the foundation of numerical weather prediction, was far ahead of the computational capabilities of the time, but it set the direction for the future development of meteorological science. The first attempt to carry out a numerical weather forecast was made by the British mathematician Lewis Fry Richardson during the First World War, and his results, which were published in 1922 in a book entitled Weather Prediction by Numerical Process, were disappointing in their accuracy, but prophetic in their vision. The development of electronic computers in the 1940s and 1950s made numerical weather prediction a practical reality, and the first successful numerical forecast was produced in 1950 by a team led by the American meteorologist Jules Charney, using the ENIAC computer at the Aberdeen Proving Ground in Maryland. Since that time, the accuracy and range of numerical weather forecasts have improved steadily, driven by increases in computational power, improvements in the observational network, and advances in the mathematical representation of atmospheric processes, and today, a 5-day weather forecast is as accurate as a 1-day forecast was 30 years ago. The measurement of atmospheric pressure on other planets and moons in the solar system has been an important objective of planetary exploration missions, as the atmospheric pressure is a fundamental parameter that determines the physical and chemical conditions at the surface and in the atmosphere of a planetary body. The atmospheric pressure on Mars, which has been measured by a series of lander and rover missions beginning with the Viking landers in 1976, averages approximately 610 pascals, or about 0.6% of the sea level pressure on Earth. This extremely low pressure, which is close to the triple point of water, means that liquid water is unstable on the surface of Mars under present conditions, and it is one of the primary factors that distinguishes the Martian environment from the terrestrial one. The Viking landers measured the Martian atmospheric pressure over a period of more than 6 years, and the data revealed a remarkable annual cycle in which the pressure varies by approximately 25 to 30% over the course of the Martian year, which is approximately 687 Earth days in length. This variation is caused by the sublimation and condensation of carbon dioxide at the polar ice caps, which transfers a significant fraction of the atmospheric mass between the solid phase and the gaseous phase as the seasons change. The pressure also exhibits a diurnal variation, similar in origin to the diurnal pressure variation on Earth, but larger in relative amplitude, and various short-term fluctuations associated with dust storms and other meteorological phenomena. The atmospheric pressure on Venus, which has been measured by a series of Soviet Venera landers beginning in the 1970s, is approximately 9.3 megapascals, or about 92 times the sea level pressure on Earth. This extraordinarily high pressure, combined with a surface temperature of approximately 464 degrees Celsius, creates conditions that are extraordinarily hostile to both human explorers and robotic instruments, and the longest-lived Venus lander, Venera 13, survived for only 127 minutes after reaching the surface in 1982. The Venusian atmosphere is composed almost entirely of carbon dioxide, with a mass approximately 93 times that of the Earth's atmosphere, and the extreme surface pressure is a direct consequence of this enormous atmospheric mass. The atmospheric pressure on the gas giant planets Jupiter, Saturn, Uranus, and Neptune does not have a well-defined surface value because these planets do not have solid surfaces in the conventional sense. Instead, the atmospheric pressure increases continuously with depth, from very low values in the outer atmosphere to enormously high values in the deep interior, where the pressure can reach millions of atmospheres and the gas transitions to a liquid or metallic state. The 1 bar pressure level, at which the atmospheric pressure is approximately equal to the sea level pressure on Earth, is conventionally used as the reference surface for these planets, and the temperature at this level ranges from approximately 165 kelvins on Jupiter to approximately 72 kelvins on Neptune. Titan, the largest moon of Saturn, is the only moon in the solar system that possesses a substantial atmosphere, and its surface pressure, which was measured by the European Space Agency's Huygens probe in January 2005, is approximately 146.7 kilopascals, or about 1.45 times the sea level pressure on Earth. Titan's atmosphere is composed primarily of nitrogen, with a small percentage of methane, and it supports a complex meteorological cycle that is in some ways analogous to the water cycle on Earth, but with methane playing the role of water. The Huygens probe measured the pressure and temperature profile of Titan's atmosphere during its descent, providing data that have been invaluable for understanding the structure and dynamics of this unique atmospheric environment. The pressure in the deep ocean, which increases with depth at a rate of approximately 1 atmosphere, or 101,325 pascals, for every 10.06 meters of depth, is another domain in which the measurement of pressure is of great scientific and practical importance. At the deepest point in the ocean, the Challenger Deep in the Mariana Trench, which lies at a depth of approximately 10,935 meters below sea level, the pressure is approximately 1,086 atmospheres, or approximately 110 megapascals. This immense pressure, which is more than 1,000 times the atmospheric pressure at sea level, presents extraordinary challenges for deep-sea exploration. As the hulls of submarines and the casings of instruments must be designed to withstand forces of enormous magnitude. The first manned descent to the bottom of the Challenger Deep was accomplished on January 23, 1960, by the Swiss engineer Jacques Picard and the American naval officer Don Walsh in the Bathyscaphe Trieste. The Trieste, which was designed to withstand the extreme pressures of the deep ocean, descended to a depth of 10,916 meters, where it remained for approximately 20 minutes before returning to the surface. The pressure at the bottom of the Challenger Deep was measured to be approximately 1,099 atmospheres, which is consistent with the expected value based on the depth and the density of seawater. More recently, on March 26, 2012, the film director James Cameron descended to the bottom of the Challenger Deep in the Deep Sea Challenger submersible, reaching a depth of 10,908 meters. And in 2019 and 2020, the American explorer Victor Vescovo made multiple dives to the deepest points of all 5 of the world's oceans in the submersible limiting factor. The measurement of pressure in the deep ocean is accomplished using a variety of instruments, including quartz crystal pressure transducers, which measure pressure by detecting the change in the resonant frequency of a quartz crystal as it is compressed. These instruments are capable of measuring pressure with an accuracy of better than 0.01% of the full-scale reading, which corresponds to an accuracy of approximately 1 to 2 meters in depth. And they're used in a wide range of oceanographic applications, including the measurement of ocean currents, the monitoring of tsunami waves, and the study of tidal variations. The industrial applications of barometric pressure measurement are numerous and diverse, encompassing fields as varied as manufacturing, process control, environmental monitoring, HVAC systems, and pharmaceutical production. In manufacturing, pressure measurement is essential for the control of processes that operate under conditions of elevated or reduced pressure, such as vacuum coating, autoclave curing, and semiconductor fabrication. In the pharmaceutical industry, barometric pressure is monitored in clean rooms and other controlled environments to ensure that the air pressure inside the room is maintained at a level that is slightly higher than the ambient pressure, which prevents the ingress of contaminated air and helps to maintain the sterility of the manufacturing environment. In the field of heating, ventilation, and air conditioning, which is commonly abbreviated as HVAC, barometric pressure measurements are used to optimize the performance of building environmental control systems as the density of air, which is a function of pressure, temperature, and humidity, affects the heating and cooling loads and the airflow rates in ductwork and ventilation systems. In environmental monitoring, barometric pressure measurements are used to correct the readings of gas analyzers and particulate monitors, which are sensitive to the pressure and density of the sampled air, and to interpret the results of air quality monitoring studies, in which changes in pressure can affect the concentration and dispersion of atmospheric pollutants. The barometer has also held a place in art, literature, and popular culture that is, perhaps, somewhat surprising for such a prosaic and utilitarian instrument. In the 18th and 19th centuries, decorative barometers were common fixtures in the homes of the upper and middle classes, and they were manufactured in a wide variety of styles, ranging from simple stick barometers to elaborate wheel barometers with ornate frames and multiple dials. The wheel barometer, which uses a float in the mercury cistern connected by a thread and pulley to a pointer on a circular dial, was particularly popular in England, where it was often combined with a thermometer, a hygrometer, and a spirit level in a single decorative frame. The barometer appears in literature as a symbol of scientific observation and rational inquiry, and it is frequently mentioned in the novels of the 19th century, where it serves as a marker of the domestic environment and of the character's interest in, or indifference to, the natural world. In Charles Dickens' Bleak House, published in 1852 and 1853, the character of Mr. Jarndyce is famously attentive to the state of his barometer, which he uses as a metaphor for the emotional weather of his household, and his repeated references to the wind being in the east have become a familiar figure of speech. The barometer also features in the works of Thomas Hardy, Jules Verne, and numerous other writers, and it has been the subject of paintings, engravings, and other works of visual art. In the realm of folk wisdom and popular belief, the barometer has long been regarded as a reliable indicator of approaching weather, and the phrase, "the barometer is falling," has become a common metaphor for the approach of trouble or misfortune. While the relationship between barometric pressure and weather is, as has been discussed at considerable length in this presentation, well established and scientifically valid, the interpretation of barometric readings for the purpose of weather forecasting is considerably more complex than the simple rule of rising pressure means fair weather, falling pressure means rain would suggest, and the amateur forecaster who relies solely upon a single barometric reading is likely to be disappointed, as often as they are gratified. The role of the barometer in the history of scientific thought extends beyond its practical applications in meteorology and aviation, for it was the barometer that provided the first definitive evidence for the existence of atmospheric pressure and the possibility of a vacuum, thereby overturning a philosophical doctrine that had held sway for 2,000 years and opening the way for the development of pneumatics, thermodynamics, and the kinetic theory of gases. The invention of the barometer was one of the key events of the scientific revolution, and its influence can be traced through the subsequent development of physics, chemistry, and engineering to the present day. The barometer also played a role in the development of the concept of the standard atmosphere, which is used not only in aviation and meteorology, but also in the calibration of instruments, the specification of industrial processes, and the definition of physical constants. The standard atmosphere, with its precisely defined values of pressure, temperature, and density at each altitude, provides a common reference frame that allows scientists, engineers, and technicians around the world to communicate and compare their results with confidence, and it is one of the many quiet but essential contributions of barometric science to the infrastructure of modern technology and industry. The use of barometric pressure data in climate science has become increasingly important in recent decades, as researchers seek to understand and quantify the long-term changes in atmospheric circulation patterns that are associated with climate change. The analysis of historical barometric pressure records, some of which extend back more than 200 years, has revealed trends and variations in the positions and intensities of the major atmospheric pressure systems, including a poleward shift of the subtropical high-pressure belts and an intensification of the mid-latitude westerly winds, both of which are consistent with the predictions of climate models. The North Atlantic Oscillation, which is a large-scale pattern of atmospheric pressure variability between the Icelandic low and the Azores high, has been shown to have a significant influence on the climate of Europe, North Africa, and Eastern North America, and its behavior over the past century has been the subject of extensive research and analysis. The southern annular mode, which is the dominant mode of atmospheric pressure variability in the southern hemisphere, describes the north-south movement of the belt of westerly winds that encircles Antarctica, and changes in this mode have been linked to changes in Southern Ocean circulation, Antarctic sea ice extent, and rainfall patterns in southern Australia, Southern Africa, and Southern South America. The monitoring and analysis of these large-scale pressure patterns, which require long and homogeneous records of barometric pressure from stations around the world, is one of the most important applications of barometric data in modern climate science, and it provides essential information for understanding the past, present, and future evolution of the Earth's climate system. The barometric pressure at the Earth's surface is also influenced by volcanic eruptions, which can inject large quantities of dust and aerosol particles into the stratosphere, altering the radiation balance of the atmosphere and causing measurable changes in surface pressure patterns. The eruption of Mount Pinatubo in the Philippines in June 1991, which was one of the largest volcanic eruptions of the 20th century, injected approximately 20 million tons of sulfur dioxide into the stratosphere, where it formed a layer of sulfate aerosol particles that persisted for several years and caused a measurable cooling of the global surface temperature. The effects of the eruption on atmospheric pressure patterns were detected in barometric records from stations around the world, and they provided valuable data for testing and validating the climate models that are used to predict the effects of future volcanic eruptions and other perturbations to the Earth's radiation balance. As we consider the long and remarkably detailed history of barometric pressure measurement, from the first tentative experiments with mercury tubes in 17th century Italy to the microscopically small MEMS sensors that are embedded in the electronic devices that we carry in our pockets, it becomes apparent that the measurement of this single physical quantity has been a thread running through the entire history of modern science and technology. The barometer has been an instrument of discovery, a tool of practical utility, a subject of philosophical reflection, and a decorative object of domestic life, and it has contributed in countless ways, both large and small, to our understanding of the natural world and to the material conditions of human existence. The atmosphere continues to press down upon us with its enormous but imperceptible weight, as it has done for billions of years, and the barometer continues to measure that weight with ever-increasing accuracy and ever-decreasing cost, providing the data that are essential for the forecasting of weather, the safe operation of aircraft, the control of industrial processes, and the advancement of scientific knowledge. The story of barometric pressure, which began with a question about why pumps could not raise water above a certain height, and which has led to a global network of instruments that monitors the state of the atmosphere in real time, is a story that exemplifies the cumulative and progressive nature of scientific inquiry, and it is a story that, it is hoped, has been told here in a manner that is sufficiently thorough and sufficiently monotonous to have served its intended purpose of encouraging the listener to drift gently and peacefully into a state of restful sleep.